In this video, you will learn how to write a matrix equation as a vector equation, solve a matrix equation, and write the solution as a vector. Also, you will determine if a vector is in span and how to fix an equation to describe a set that would yield a consistent solution. So, what are we learning today? We are learning I forgot to put a title, but we are learning the matrix equation. All right, the title. AX equals B. Okay, so before we go any further, let me ask you some of these questions. Did you know that there are three ways to view a linear combination of a vector? Linear combination of vectors can be viewed as system of linear equation, vector equation, and matrix equation. But before we go any further, we need to go some very important definition. So consider an n by n matrix A with the columns vector A and vector x in the span of Rn. So matrix multiplication and linear combination. The product of A and vector x, denoted as A times vector x, is the linear combination of the columns of A using corresponding entries and vector x as weights. So vector A times vector x can be also written as this. And a thing about multiplying matrices is you got to test if it's possible. So yeah, so this is a note that a times vector x is only defined if the numerator of the columns of A equals to the number of entries in X. So a matrix times a matrix is defined as long as the numerator of columns of the first matrix A equals the number of rows of the second matrix. So what does that mean? Um, let's say you have a matrix by m by n, and then you have another matrix, it's by n by r. So these two numbers has to be the same. If they're not, then it's not, you can't multiply those two matrices. And then your final outcome will be expressed as m by r. So this number times this number. So yeah, always check if you are able to multiply two matrices. So let's do a quick example. Multiply the two matrices if possible. So can we multiply this two matrix first? I'm going to determine. So this matrix here, how do you measure it? It's a 2 by 3. And then this matrix here, that can be measured as 3 by 1. Because remember, we always go by rows by column, right? Okay, so can we multiply these two matrices? Yes, because these two numbers are the same. And then the final outcome is this number by this, so 2 by 1. Okay, so your final matrix will be a 2 by 1, so it would look something like this, 2 rows and 1 column. So what do we put in these numbers? What do we put? So how do you do this is you kind of have to visually do this. So what you're doing is multiplying this this row by this column, right? And then whatever that answer is, you're going to put it here. And then you do this row multiplied by this column. Whatever that answer is, you put it in here. So let's do that. So let's do this part. This row, 8, 3, -4, multiplied by the vertical column 1, 2, 3. So that's 8 times 1 plus 3 times 2 plus -4 times 3. Okay, when you put it all together, you should get my calculator. So I wrote it down and then we did it. What did you get? You should get two. So when you do all this work, you should get two. So this number here will be two. And then what about the other number? The other number is, now we're going to do this row times it by this vertical column. So that would be 5 times 1 plus 1 times 2 plus 2 times 3. Okay, when you put it all together, you should get an answer of 13. This is 213. Okay, so this is your final answer. So that is how you multiply two matrix. You have to make sure it's possible, and then your final outcome is this number by this number. Okay. Let's keep on talking about continue with the lecture. So connecting system of equations with matrix equations. So let's say you have a system of equation, x plus 2y plus 5, and the other system equation is 2x minus y plus 3. Do you know you can write it in two other forms, such as vector equation and matrix equation. So in vector equation, it would be x times 1, 2. There should not be a divide, it should just be 1. Okay, and then you can also then plus y, and then the vector 2 comma negative 1 equals to the vector 5 comma 2. So you can rewrite this as a vector equation, and then you can also write this as a matrix equation. It would be matrix 1, 2, 2, negative 1 times the matrix x comma y, and it spits out 5 comma 3, so there should be 3 here. Okay. So yeah, just keep note of that because we're going to use that will come in handy when we do our examples. Row reduction and consistency. So we can use row reduction RREF to help us solve the system. Take the matrix A times vector X equals vector B, has the same solution set as the vector equation. So this vector equation in turn has the same solution set as the linear equation whose augmented matrix is this. So let's look at this example. We have this system equation, 8x1 plus x2 equals 2, 5x1 minus 4x2 equals 4, and then x1 plus 3x2 equals 1. So you can write it as three different forms. You can write it as a system equation, which we already have, which was given. You can write it as a vector equation. So this would be a vector equation. And then you can also write this as a matrix equation. Okay. And then what you want to do is write somehow do augmented matrix and solve using row reduction. So what is row RREF? Basically, you have these diagonals or these pivots, and then everything below 1 is 0, and everything above 1 is 0. Okay. Since the pivot 1 is located in the B's, the system is inconsistent, yielding no solution. So this would be no solution because pivot 1 is located in the B's. Okay. Okay, vector span and matrix equation. So this means that the matrix equation A times vector X equals vector B has a solution if and only if vector B is a linear combination of column A. So the existence of a solution theorem states that a system is consistent if the columns of A span in R raised Rm. In other words, for each B in vector Rm, is a linear combination of the columns of A when the coefficient matrix A has a pivot position in every row. So if we were asked to determine if B is in the span, all we have to do is verify that A times vector X equals B is consistent. Okay, so we'll do an example. So let's do example one. Write the linear combination of this as a matrix times a vector. So how will we do that? We would write it out as so yeah, you can rewrite this as the similar to this vector one vector two vector three is equal to a b1. Okay, so what you're doing is basically you're multiplying coefficients. So your coefficients are -2, 4, and -8. By the vector v1, v2, v3. Okay, so is this even possible? This is a 1 by 3 times 3 by 1. So yes, it's possible because these two numbers are the same. Your final answer will be a 1 by 1 matrix. Wait, so this would be the answer. Okay, let's move on to next example. So write the system equation of this as A, matrix times a vector as A, and B, matrix equation vector A times vector B equals vector B. Okay, so let's do part Roman numeral I or part A. So you can rewrite this as a matrix times a vector would be expressed as x1 times 1 times -2 plus x2 times 2 times 2, 5, and then that's going to equal to vector 7, 4. So this is like your B, and this 2 matrix is your A, and then you have this x1, x2, that is like your A, your X, right? Okay, so that was part A, and then part B says matrix equation A times X equals B. So basically, you're just going to write it out as so part 2, you can rewrite this as 1, -2, 2, and 5, x1, x2 equals to 7 fourths. Okay, so this is vector A, vector matrix A times vector X equals to vector B. This theorem, I'm just going to read it. It's basically what we just said. So basically, if A is an n by n matrix with columns A1, A2, And if vector B is in the span of Rn, matrix equation A times vector X equals vector B has the same solution set as a vector equation of this, which in turn means that the augmented matrix has the same solution. So we can view a system equation three ways: system of linear equation, vector equation, and matrix equation. All can be solved the same way with row reduction. So let's look at example A. We have vector A equals that, and vector B, which is this. Is the equation A times vector X equals vector B consistent for all vector B? So what you have to do is augment it and then put it in RREF. So let's do that. So first part, do this part. So that would be expressed as 1, -3, 2, and then this would be B1, B2, B3. Okay, so we got to put it in RREF. So the first thing I would do is maybe make this -3 into a 0. So how would I do that? You would have to multiply 3 times row 1 plus row 2. And then that'll give us your new row 2. So I'm just gonna, you can pause the video and do the work, but I already did the work, and I get 0, 1, 1, and then this is gonna be 3b1 plus b2. And then column 1, I mean row 1 and row 2 stays the same, so this is 1, 4, 5, b1, and then this is 2, 8, 10, b3. Okay. Then what I'm going to do next is make this 2 into a 0. And how do I make that 2 into a 0? You're going to multiply. So 2 is technically in row 3. And to make that to 0, you're going to multiply -2 times row 1 plus row 3. And that'll give us your new row 3, and then that will make this 2 into 0. So you can pause the video and then do the work individually, but since I did the work, it gives us 0, 0, 0, and then the side is equal to -2b1 plus b3. And then this is going to be 0, 1, 1, 3b1 plus b2. And then this is going to be 1, 4, 5, b1. Okay. So you can stop here. So if we is the equation A times vector X equals vector B consistent for all B, you could stop here because you have a false statement. 0 does not equal to this. So you can say no. AX equals B is not consistent. For all vector B. Unless we can make it true, right? So unless you can say 0 equals to -2b1 plus b3, then yes. Okay. Let's move on to existence of solutions. So it's just more theorems. The existence of solution The equation A times vector x is equal to vector v has a solution if and only if vector v is a linear combination of the columns of A. In other words, is vector b in span of that, which is equivalent to A times vector x equals vector b, consistent. The columns of A span R raised to the m means that every vector b in the span of Rm is a linear combination of the columns of A. So the set vector v1, v2 is equal to the span of Rm. If A is an m by n matrix, then either all are true or all are false. So yeah, for each vector b in Rm, the equation A times vector x equals vector v has a solution. Each vector b in R to the m is a linear combination of columns of A. The columns of A span R raised to the m. A has a pivot position in every row. So it's basically like the last example. If it's consistent, then it has, yeah. So let's do an example. Vector A equals that and vector B equals that. Show that the equation A times vector x is equal to vector B does not have a solution for all possible vector B, and describe the set for all vector B for which A times vector x equals vector B does have a solution. So what do you have to do? You're going to have to put it in augmented form. So we have matrix A and matrix B, right? So what you're going to do is write it out like this. Right? And then what we're going to do is put it in RREF form. So let's make this -3 into a 0. So to do so, we're going to multiply that by 3 times row 1 plus row 2. And that will give us your new row 2. You can pause the video to do the work, but you do get 0, -7, -6, and then this would be 3b1 plus b2. And then over here, this stays the same. So 1, -3, -4, b1, and then you have 5, -1, -8, and this is b3. Okay, then what I would do is make this 5 into a 0. So how do I do that? It's going to just be -5 times row 1 plus row 3. And that gives us your new row 3. So when you do that, you get 0, 14, 12, and you get -5b1 plus b3. And over here you get 0, -7, -6. You have 3b1 plus b2. And you have 1, -3, -4, and then you have b1. Okay, then find the pivot position. All we need is REF. So we don't really have to make, so what we have to do is just get more pivot ones. So maybe the next thing I would do is make this 14 into a 0. So how would I do that is I would do 2 times row 2 plus row 3, and that should give you your new row 3. When you do all that, you get 0, 0, 0, straight line, and then you get B1 plus 2B2 plus B3. And then over here you get 0, -7, -6, and then you get 3B1 plus B2 and you get 1, -3, -4, and you get B1. So you could stop here because this is a false statement. 0 does not equal to that. So what you can say, so just look at so 0, it says false, so 0 is not equal to B1 plus 2B2 plus 3B3. So this would be no solution. And then, but if you can make it true, if you can say if 0 does equal to B1 plus 2B2 plus B3, then AX equals to B has a solution. Vector B. Okay, let's do more examples. So let's do this example. So let vector v1 equals to this, vector 2 equals to this, and vector 3 equals to that. Does v1, v2, v3 span R3? So what they're really saying is to span R3, we need 3 pivots. We need 3 pivots, a pivot in every row. Okay, so first we got to do our augmented thing. So we're going to do ax equals b. So it would be 0, 0, -2, and then this would be 0, -3, 8, 4, -1, -5, and vertical straight line, and then this would be A, B, C. Okay, so maybe what we could do is the 0, 0, I don't want those zeros. Maybe we can switch columns. Maybe we can switch, no, columns, rows. Maybe we could switch row 1. Here's row 1, right, with row 3, right? So switch them. So row 1 goes to row 3, and then row 3 goes to row 1. So that would be -2, 8, -5, and then C. Row 2 stays the same. And then the last row would be 0, 0, 4, and 8. Okay. Then what you want to do is try to get your pivot. Maybe make this -2 into a 1 and make this -3 into a 1 and make this 4 into a 1. So all we got to do is multiply by scalar, and we can multiply scalars more than once. So we could do a scalar more than once. So you could say -1/2 row 1 gives you row 1. And then this would be -1/3 row 2, and then that gives you row 2, and then 1/4 row 3 gives you new row 3. When you do all the work, you get 1, 0, 0, -4, 1, 0, 5/2, third, 1, and then this is going to be -C/2, -B/3, A/4. So let's go back. So do we have, we only need 3 pivots, pivot in every column. Do we have these pivots? Yes, we have 1, 2, 3, and it's in every column. So you can say yes. It spans R3. Since 3 pivots, 1 in each row. Okay, let's stop here. We'll do another more examples in the next video. So I will continue this.